Yeah,
Yeah,
exactly. Yeah, that's very important to
that
mention.
picture was in my book too when I was studying 30 years ago.
In 1986, there was a tragedy which happened, which was the Challenger space shuttle
Yeah.
explosion.
But what kind of materials are used below 120 Kelvin, and what are the applications for that?
Right.
Hi, Mohammed.
Hi, Peter. How are you doing?
Fine. Welcome to the podcast, Everyday Metallurgy.
Thank you so
Today,
much.
today we are going cold. In Denmark, winter is getting closer, but that's not really cold because 0 degrees is a paradise compared to where we're going today. We're going cryogenic. And very often materials behave in another way when temperature goes low. And what are these mechanisms that are causing that? That's our deep dive today. Mohammed, will you give an introduction to yourself, your background, and where you are today?
Thank you so much, Peter. And I'm thrilled to be at Everyday Metallurgy because that's what I do every day for many years now. So my name is Mohammed Nayeem, and I'm currently a principal investigator in Leoni Academy of Materials. This is a new research institution in the Shenyang, China. And throughout my education, undergrad, master's, PhD, I did metallurgy, so I really love it. And in 2020, I got my PhD from City University of Hong Kong, also in metallurgy. Then I have been working in Hong Kong, then in UK, University of Birmingham, and now I'm here. And so this is my journey. So during this time, I have been mainly for the past 10 years working on cryogenic behavior of materials, and mainly by using techniques such as in situ neutron and synchrotron diffraction.
Yeah.
Yeah.
So if we look deeper into what this is, what is happening with materials when temperature goes low? Can you describe, give some insight to it?
Right. So as you mentioned that temperature in Denmark, similarly in Shenyang, we also get very cold winter. So the temperature goes down to minus 30 degrees Celsius over here.
Oh, we
So
don't get that here.
which seems very cold.
Yeah.
And many things happen with materials, engineering materials, which are used in many applications when they experience such low temperature. So, and I think I would start with going to like not too low, but the low which we usually achieve, for example, closing to the freezing temperature, say 0 degrees Celsius. And usually when temperature decreases, so materials become brittle. That's the understanding. So what does brittle mean? It means so they lose their energy absorption when they experience any kind of impact, right? So if there is any kind of crack, it can't be stopped because they cannot absorb they don't have enough capability to absorb that crack. So, and but it's much more deeper than that, because usually in metallurgy, in material science, we talk about things which are happening at the atomic scale, what is happening with the atoms. So their diffusion becomes slower. And then we have these different kind of defects, say dislocations. So they also get affected at low temperature.
Yeah.
So do you want me to talk about some examples like of low temperatures?
Yeah, because before we dig into the material, are there any historic examples that people could relate to, and maybe where it has been fatal or new development was needed to mitigate?
Right. So that's excellent, because I love talking about history. I mean, this is like, if I would not be a metallurgist, I would definitely be gone into history.
Yeah.
So I can give some historical accounts of significance of low temperature, what it can lead to.
Mm-hmm.
So one of the most famous example I can start with is from over a century ago, which is of Titanic. And I think a lot of people have watched Titanic movie, and we know what happened to Titanic.
Yeah.
So when Titanic had when it was built, so it was dubbed as unsinkable ship.
Mm-hmm.
And then it sank on its first journey.
Yeah.
And now the thing which we know that it hit across iceberg, and ultimately it lead to water pouring in and it sunk. But now metallurgists have done analysis of the steel which they took from the hull of the Titanic wreckage,
Mm-hmm.
and they did tests on it. Basically, its fracture toughness,
Yeah.
how much energy it can absorb with lowering temperature. So the steel which was used in that ship, that is very different what we normally now modern ships use. So modern ships, this decrease in so it almost drops significant energy absorption close to -20 or so. The modern ships like the steel can like have more
Yeah.
capability. But if you really look at we will have some reference, and we can see that for that steel around even room temperature, it was almost close to zero energy absorption. So what happened that when it hit, because it cannot absorb much energy, so because of this impact, when it happened, so of course it was with this iceberg, but ultimately that lead to rapid crack, and that led to massive flow of water inside, and which ultimately sank it. So that is one of the first historical example.
Yeah.
Then we can move few decades ahead into Second World War, and there was these Liberty ships which were built for war purposes, and this was the first time that they were completely welded. Like so, these ships they were made. I mean, they were welded across.
Yeah.
You know, like to make them very fast, and
Mm-hmm.
so uh, then they were sailing in the ocean. So many of them actually ruptured into half. I still remember when I was undergrad student that we had in our metallurgy book, mechanical metallurgy book, where there was this image of Liberty ships being split into half in the middle.
Yeah. In a
So
harbor.
yeah,
Yeah.
exactly. Yeah, that's very important to
That picture
mention.
was in my book too when I was studying 30 years ago.
Exactly. So I seen the same image, and hopefully we will be able to put that up, if not from that book, maybe from somewhere else.
Yeah.
So so the initial thought was like it happened because of weld failure, because this was a new experience, like the whole ship is built by welding.
Yeah.
But it is very interesting that ultimately it turned out like that was not the cause. So the cause was, I have to now talk about a person. So there was a person, her name was Constance Elam, later known as Constance Tipper. She was working at Cambridge University. Actually, she had number of publication with G.I. Taylor. I mean, very famous and important with dislocation and the deformation. So, so she was responsible for studying those ships. I mean, she took samples from them, and they did their tests. And she actually coming up with the test now it is known as Tipper test. And basically, she shown for the first time that instead of weld, because weld, if the crack initiate, it should be arrested somewhere. But in this case, it just start and it just like completely go into the base itself, not just in the weld. So her point was that when at low temperature, there is a certain temperature at which the steel become brittle. So it cannot remain the same as it is, say, at ambient temperature. And the ships which they were experiencing the temperature which was close to -2 degrees centigrade. I mean, close freezing point.
Yeah.
So that was the cause of that. And that's how we have now field of this ductile to brittle transition. And now we know about it very well.
Yeah.
Okay. Now I can come to third example, which is, so we talked about ships, and now we can talk about sky ships. We can talk about the space shuttle. So in 1986, there was a tragedy which happened, which was the Challenger space shuttle explosion.
Yeah.
So it took off from the coast of Florida on January 28, 1986. And within 73 seconds, it exploded. And all the 7 board members on the space shuttle, they were killed. So to understand what really happened, so there was a commission set up by, at that time, president was Ronald Reagan. So he set up a commission called Rogers Commission. And it included, so that commission included a couple of very famous people. One of them was Neil Armstrong, the first man on moon.
Yeah, on the moon.
And the second one is my favorite scientist, Richard Feynman. So during that investigation, Richard Feynman, I mean, like we know, he was a genius. So he came up with an idea, and he took an O-ring from the seal of this fuel tank.
Yeah.
And in front of this whole inquiry, and he put it in a C-clamp, and he fastened it, and you can see flexibility in the O-ring. Then he had iced water beside him. So he dipped that O-ring inside the iced water and took it out, and now he put it inside the C-clamp again. But this time when he did that, there was no flexibility.
So it broke.
So it could not like do that compression which was needed for that fuel tank to work. So now, so his conclusion was, because usually the previous missions which happened, they were usually at high temperature, which is like 12 degrees centigrade or so. But the day this Challenger took off, the temperature over there was around 0 degree minus 1 degree Celsius. So it was a significant difference compared to normal voyages which happened in the past. And so it was quite like, maybe it would not have been avoided because no one knew like what's going to happen. But ultimately, that was the cause of that space shuttle explosion.
Yeah.
So these are, I mean, I really love talking about this kind of stuff. Like we can go on and on forever. But I think I will stop with. But the point of all of these examples is to show how significant low temperature is in our applications. I mean, these are massive and very, very sophisticated. For example, say the space shuttle, and then low temperature can have such a huge influence, which not only cause this massive, I mean, damage to these things, but also cost lives as well. So, and also embarrassment as well at the end. So at the end, we do have to consider like how materials behave at such, but this is not that low temperature, right? I think what we'll be talking, as you mentioned in the beginning, we're going to be talking about much lower temperature, because this temperature which you talk, we can achieve, I think, in Denmark as well. I mean, this is very common temperature across the Europe and in other countries as well.
We are going to dig into cryogenic temperatures. So how do you separate just cold from cryogenic? Where is the threshold of that?
Right. I think that's very important, because I have seen people using these terms interchangeably. So it seems like people call cryogenic cold, low temperature, ultra low, very low. But so sometimes it's important to like mention that is there a boundary? So yes, there is a boundary. So the boundary is set at 120 Kelvin. So why 120 Kelvin? So anything which is above 120 Kelvin, so we can say from freezing point up to 120 Kelvin, that is low temperature or cold or whatever you call it.
Mm.
And anything which is below 120 Kelvin, that's cryogenic.
Yeah.
So why?
Mm.
So because all the mostly, actually not mostly, like all of refrigerants, their boiling point is above 120 Kelvin, right?
Yeah.
While all the permanent gases,
Mm.
their boiling point is below 120 Kelvin. We take like hydrogen, oxygen, nitrogen, helium, they're all below 120 Kelvin. So
Yeah.
this is the line, this is the boundary below which we call 120 Kelvin below. Whatever like lowest we can achieve, that is
Mm.
cryogenic, and above that it's low temperature or cold.
Thank you. Very clear. Now, next time I hear people use the expression, "Oh, it's super cold." No, it doesn't exist. But it's mega super cold. No, it's cryogenic or not. That's. Thank you. But what kind of materials are used below 120 Kelvin, and what are the applications for that?
Right. So of course, as we started with, I mean, the focus of your podcast, Everyday Metallurgy, of course, we ultimately talk about applications.
Hmm.
And there are many applications. I mean, the examples which I gave, that was of low temperature, right? Because that was close to freezing point of water. But we have many applications which exist at cryogenic temperature. So we can start with, for example, energy sector. So fusion reactors, tokamak, they have number of components which function at cryogenic temperature.
Yeah.
The most important is superconducting magnets. So superconducting magnets, they operate at liquid helium temperature, 4.2 Kelvin.
Yeah.
But it's not just superconducting magnets, but it's also thermal shield, which is around liquid nitrogen temperature. Then there are cryo pumps. So this is one example of energy.
Yeah.
Second example we can have from medical field. So magnetic resonance imaging, MRI. So it operates at liquid nitrogen temperature. So for it to function, we use liquid nitrogen. Then we have example from Space Shuttle, for example. So it have number of components. For example, if we are going to a mission at Pluto, like the planets which are far from Sun, if we're going there, the temperature is going to be lower.
Yeah.
So to take a mission to Pluto, its surface temperature is 40 Kelvin.
Yeah.
So whatever material you have to use, they should be able to bear that temperature. It's not like they will touch and they will boom, right?
Yeah.
So we need materials for that.
Yeah.
Then another thing I would like to mention is about, because now climate change, I mean, not just now, but it has been a huge issue for a long time now, and we really have to do something about it. And now there is a lot of focus on hydrogen-based economy, right?
Yeah.
So hydrogen itself, like if you have to handle it, so its boiling point is around 25 Kelvin. Yeah, exactly.
Yeah.
Exactly. So again, so that's a cryogenic area. And then, so you have to store that. We have to transport it. Okay. So for that, we do need in our labs, for example, TEMs, we use liquid nitrogen. So again, like we have to have these containers which can sustain that. So I mean, there are abundant applications. I came across a while ago that Airbus is going to install a liquid hydrogen tank in their plane, again to cut on emissions. So these are, I mean, few examples, but as you can see that across medical, across energy, across space, across our labs. So there are plenty of applications which require materials which can operate at cryogenic temperature. So you asked about what kind of materials. So that's all it is about. I mean, ultimately, like we want to use materials which can survive. So one of the most commonly used material at cryogenic temperature is authentic stainless steels.
Yeah.
So
304, 316.
Exactly.
Yeah.
So they are the most widely used in these applications because they have been studied for such a long time. They are reliable. They can sustain and they don't become brittle at such low temperature, like say we're operating at liquid helium temperature, which is 4.2 Kelvin. So they remain good. They have good strength and very good ductility at such low temperature. But now we have other emerging materials as well. So I think we can talk about one of them, high entropy alloys. So there have been
Yeah.
lot of interest in high entropy alloys,
Mm.
and one of the reasons high entropy alloys became so interesting, and there was a huge upward shift in high entropy alloy was there was publication coming out in 2014 about high ductility in high entropy alloy at cryogenic temperature,
Yeah.
at liquid nitrogen temperature. So since 2014, if you see like how really high entropy alloy field started, like suddenly like it became exponentially like growth in research and in projects. So that was the year when that paper came out. And since then, there have been a lot of alloys which have been identified because they not only have good strength at, because the strength usually increases when we decrease its temperature, but they also increase their ductility. So I think we'll talk about that in a bit.
Yeah.
So I think I can stop here. So
Yeah. So the alloys we've been talking about now, the stainless steel types, they are austenitic. The high entropy alloys, they are typical single phase, also austenitic. Has the cryogenic properties something to do with the microstructure? It smells like there is a connection. Can you disclose a little more?
exactly. So the main thing, exactly what you pointed out, because the structure of austenitic stainless steels and high entropy alloys, which shows very good properties at cryogenic temperature. And we're talking about mechanical properties, by the way. So the common thing is crystal structure. They both are face-centered cubic, FCC. And usually the materials which have BCC structure, they usually become brittle at low temperature. So they have a very sharp ductile to brittle transition temperature. We can talk about some very famous BCC, for example, tungsten. Tungsten's ductile to brittle transition temperature is above room temperature. Actually, it's around 300 to 400 degrees centigrade. It's much higher. So while for, say, ferritic steel or for iron, it's around just to the freezing point of water. So it's like close to that. So below that, at some point, it becomes completely brittle. But that kind of this kind of trend does not exist for FCC. They remain ductile. We don't see really this kind of sharp ductile to brittle transition in FCC materials. They remain ductile all the way down to the lowest temperature, which we have tested. So exactly, it's a crystal structure which is responsible for that. And that ultimately can be linked to how dislocations behave, which kind of dislocations they have, right? If they can have more slip systems, which is the case for FCC, they can have edge type dislocations, which play a role in that. So this is more technical, but by the nature of the crystal structure, they retain their ductility if they don't increase it. For example, high entropy, they do increase in ductility, but for example, stainless steel, austenitic stainless steel, they don't show increase in ductility, but they still retain very good ductility down to liquid helium temperature.
So is it because the slip system in an FCC is easier and doesn't act or need energy? So you have the sliding in twinning, for instance.
Right. So the thing is, because FCC can activate multiple slip systems. So the more slip system you can activate, the better. I mean, so dislocations have to move. So that's how deformation works. So the more slip system options you have, so the better there are chances that it will not be blocked, because when you go to cryogenic temperature, the dislocation motion become frozen. So if you can have more chances of creating that, of course, that's helpful. But of course, it's not just dislocation slip, it's also other kind of mechanism. You mentioned about twinning, and especially at cryogenic temperature, twinning become prominent. Because when we go to low temperature, so pulse stress, which we also call lattice friction stress, that increases. So all the materials, which most of at least like, but in BCC, FCC, HCP, when compared to ambient temperature at cryogenic temperature, they always show higher strength. That's because their pulse stress that increases.
Yeah.
Because basically dislocations are kind of frozen, so to speak, right?
Yeah.
So it takes more force for them to push through.
Yeah.
So the yielding strength increases.
Yeah.
But at the same time, so the critical stress which you need for dislocation slip to occur, that also increases, right? But at the same time, twinning is different. So twinning is more or less independent of temperature. So it usually need higher critical stress for it to activate. So that's why in many materials, we may not have twinning at room temperature, at ambient temperature. But when you decrease temperature and the dislocation slip become more difficult and it need high stress, but twinning that retain the same critical stress. But now because the pulse stress have increased, so the material is more stronger and it is able to attain that higher stress which is needed to activate twinning. So by combining these things, and then of course, like in addition to that, we can also have phase transformation at cryogenic temperature. So these are things which are interlinked, and we can have multiple mechanisms which can ultimately lead to this better ductility in FCC materials.
Yeah. I remember I read a post from you about your trials in where you shared that you have been measuring this in situ on very small scale with using neutron diffraction. I was so amazed, and I would like if you could share some of these stories with the followers, because that is wow.
Right. Perfect. Of course, I would love to share that. So I mean, for the last 10 years, I have been using neutron and diffraction to study different kind of alloys, high entropy alloys, steels, including some aluminum alloys. So I would like to first say what is difference. I mean, what we can obtain with neutron diffraction, which may not attain with other things. So I also use synchrotron. Synchrotron is simply high energy X-ray. So we can have X-ray source in our lab, but then we can go to really massive facilities. For example, ESRF, which is European Synchrotron Radiation Facility in France. Similarly, there is in Germany, in UK we have. And so these are massive facilities where you can study in situ behavior of materials, which is because ultimately we have to put them in service. So we have to study in service, like how or in real time, how they will behave. But you can also do in situ experiments, by the way, in your lab as well. For example, I have seen many labs now have some kind of a stage in TEM, transmission electron microscopy, where they can do tensile experiments in situ, and they can also observe how dislocations are moving, how twins are forming, how transmission is happening. That's very, very cool. Always like really amazing.
But it's a bit difficult at 120 Kelvin or below.
Right. So yeah, it's still very difficult to do that at such low temperature, but still some labs now have developed this system, especially national labs, where they can do at low temperature. But the issue with doing inside the TM, because your sample is really, maybe it is just 1 grain, maybe you're within a grain. So basically, and the materials, when we put them in real service conditions, they are usually very big materials. So we have to have effect of other grains. And we also know that how slip activates, how twinning activates, that also depends on orientation, right?
And the neighbor grain.
Exactly, neighbor grain. So basically, we want to look at bulk behavior, how they behave. So the other option is we can do synchrotron, for example, we can do in situ, but in that still we are limited, like we can do hundreds of micrometer, sometimes we can go up to millimeters, but depending on which material, for example, titanium or aluminum, you can go to few millimeter. But if you have to do steel, depending on what energy you're using, maybe 1 millimeter maximum, you can penetrate. Neutrons, because so X-rays interact with electrons, and their scattering cross-section is proportional to atomic number, right? Neutrons, on the other hand, because they are neutral, so they just pass straight and they interact with the nucleus.
Okay.
Right? So because they are neutral, so they can go to the nucleus. And also because they're heavy, so their impact is more. So we can probe bulk behavior. At the same time, also because neutrons have magnetic moment, so we can also study magnetic materials. While with X-ray, for example, we cannot do that because we can just study, So these, and also because neutrons are interacting with the nucleus, we can also we can distinguish between isotopes. So there is a huge work which people do with hydrogen deuterium. So they can substitute some parts, especially in protein folding community. So it's really, really interesting. But okay, that's I think going too far away. But I do love talking about neutron. Which right. So we have two facilities as far as I know around the world where they have cryogenic load cell. What does this load? This is a massive machine. So hopefully we'll be able to show an image of that. So it's a massive machine. It's put on a sample table. So sample table, you can imagine like it's also massive. Inside a neutron beam line. So this is basically we can reach temperature of liquid helium, 4 Kelvin, and we can study bulk samples. So with neutrons, for example, with steels, with high entropy alloys, we can use 5-6 millimeter thick samples. So we can really gauge millions of grains or maybe like more. And we can have a very big beam. In that way, we can really look at the bulk behavior. And also in situ. So when you're cooling, so you're measuring your data constantly. Similarly, when you're loading, tensile loading, you're starting sample. So again, you're mining data continuously, so you know really what is happening. So these neutron facilities, they are few around the world. And I mentioned that there are two of them which have cryogenic load cell. One is ICIS neutron and muon source in England. Another one is J Park in Japan Proton Exchange Research Complex. So I have done a lot of experiments in these two facilities because most of my work deals with the in situ tensile deformation with neutrons. So basically, these are the setups which we use, and we measure like how their mechanism is changing, and we can really see in situ what is happening. So just to our very first experiments when we were doing, so we had this so-called Cantor alloy, this consisting of chromium, manganese, iron, cobalt, nickel in three atomic 5 elements.
The first generation high entropy alloy.
Exactly. So we were cooling, cooling it from room temperature down to liquid helium temperature. And we saw, so because it's FCC structure, so we know which peaks are there. So those were there. But when we were cooling around 80 Kelvin, we saw there was a new peak come up. So which is 110. So if I'm sure like the audience would know that 110 is forbidden in FCC. You don't have that. And that was the only peak, additional peak which we saw. So it appeared and it sustained down to the lowest temperature. But when we warmed it up, again, it was there until 80 Kelvin. And when it went above 80 Kelvin, it disappeared. So that was very strange to us. But it took us a while to figure out. We did a number of other tests. And ultimately, we found out that was because of the change in magnetic nature of this alloy. So when we did the same experiment with, say, X-rays, we did not see that peak come up because neutrons can interact with, it's not just nuclear interaction they also have magnetic interaction. And that peak was related to magnetic ordering of the material.
So there was no change to BCC.
No, there was no change to BCC,
Oh,
and
yeah.
that was the only peak which survived, which was there and which lasted, and then it disappeared. So, so it was very interesting that how in situ we would have never known that, because when we do, for example, this experiment in labs, so we do tensile tests, or we do cool it, then we do test, then we bring it back, we make TM sample or EBST or whatever, and then we take it, put in microscope. But of course, it would disappear. It would not be there anymore. If you don't do in situ. So these are the advantages which we can get out of these kind of facilities.
Yeah.
Yeah.
And the dislocations, can you see them in situ on the run as well?
Right. So now, for example, how people look in TEM, and you can visually see a dislocation.
Yeah.
When we do these kind of experiments with, say, neutron diffraction or synchrotron diffraction, we don't see dislocation per se. But because all we see are diffraction peaks and how they change when you cool or when you load. So basically, these Bragg's peaks, they are fingerprints of a material, because we talked about crystal structure. That's really what controls everything. Now, these diffraction peaks, how they change. So if you apply load within the elastic limit of a material, so you will see your Bragg peak will shift. There will be no other change. It will just shift because it's strained. So because of that, it will move.
Yeah.
But if you go beyond yielding point, you will see the peak will broaden, which is because of grain substructure. And that is contribution coming from dislocations, also because of grain refinement. Also, if there is, say, formation of some faults like stacking faults or twins, that can also cause that. Then we also see diffraction peak, it can change its intensity. Intensity also changes because that is related to texture. Because when we deform a material, so the grain orientation, they reorient, right? So what we call preferred orientation. So because of that, their intensity changes. So basically from this, ultimately, we can estimate dislocation density. So we have number of parameters which we can use, and there are different programs which can use to estimate dislocation density, stacking fault density, twin fault probability, and so on, by fitting these peaks. And because we have throughout the process, of course, you can have a trend afterwards, and you can see when the dislocation density, how like quantitatively, and how it is changing during deformation. So yeah, not physically we can't see, but ultimately you have information what you would need to really describe how your material is behaving.
Yeah. When working with high entropy alloys, you said you started with the Cantor, the father of high entropy alloys. Did you take a further step? Have you been looking into other high entropy alloys, and have you find some optimum designs to be better at cryogenic temperatures?
Right. So we do look at hosts of materials, including high entropy alloys. So we looked at a number of variants of Cantor alloy, which is removing manganese, or chromium cobalt nickel, which have been studied a lot because it shows much better properties than vanadium cobalt nickel. But we also looked at BCC high entropy alloys as well. And it's interesting that BCC high entropy alloys, they behave a bit differently what we expect from BCC metals or BCC conventional alloys.
Yeah.
So BCC high entropy alloys, they don't become brittle. I mean, at least not at liquid nitrogen temperature. So some of them, for example, again, one of the most famous BCC high entropy alloy, which is also known as Shinkov alloy, this zirconium, hafnium, tantalum, titanium, right?
Sounds
niobium.
expensive.
Yeah, so that maintain its ductility I mean, it does not become brittle at least up to liquid nitrogen temperature, but it does become brittle to very low, I mean, say close to liquid helium temperature. So it have much high, I mean, I would say like a lower ductile to brittle transition temperature compared to other BCC system. And now there are a number of studies which say that maybe it's the activation of or change of dislocation mode from screw to edge, which is causing this. So this is interesting field and it's like really growing. But yeah, we did study, to answer your question, that we did study different kind of FCC as well as BCC high entropy alloys. And we saw that most of them, like especially FCC, behave in a very good way at cryogenic temperature. Some of them do, actually majority of them have twinning and phase transformation as well at cryogenic temperature. But so deformation twinning. So for example, Cantor alloy at room temperature, it only have dislocation slip. But when you go to cryogenic temperature, it also have twinning and stacking faults, right? It forms during deformation. Chromium cobalt nickel also lead to some phase transformation as well. So it transforms from FCC to HCP. So we studied, we had a couple of paper on that. Then, but we also came across when in cobalt nickel, and at 15 Kelvin, it have higher ductility compared to room temperature, but still it have only one deformation mechanism, which is dislocation slip, because its stacking fault energy is very high. So stacking fault energy is kind of signature, which kind of mechanism you operate. So I think I can just say very quickly that so basically the energy which you need for any kind of stacking fault to form. So if it is higher, so it means it may not form. So but if it becomes lower, so you can have from dislocation slip, you can have stacking fault, you can have deformation twinning, you can have phase transformation, multi-acidic phase transformation. So stacking fault energy depends mainly on composition. So you can change element and stacking fault energy can, for example, you can increase, decrease. So you can design material which can have specific mechanism by changing allowing element. But
so
another
is it,
thing,
is it like I mix small atom with medium-sized atom with big atoms, and when I mix that and it's not really ordered and the crystal structure is kind of squeezed all over, is that when you reach high stacking fault?
not necessarily.
Or what is that phenomenon called?
Right, because stacking fault energy is more linked with crystal structure. Okay, it's a bit hard to like say, because there are certain elements which decreases stacking fault energy, certain that which increases. If we compare, for example, say Cantor alloys compared to say one which have lower stacking fault energy. So Cantor alloy have stacking fault energy of around 30 millijoule per meter square. That's at room temperature. Now, if we go with say one other alloy, which is chromium cobalt nickel, and a ternary medium entropy alloy, that have around 20 millijoule per meter square. So that have lower stacking fault energy. So you remove manganese and iron, so you can decrease stacking fault energy. But if you, for example, dealing with nickel alone, nickel have very high stacking fault energy. It have around 125 millijoule per meter square. So, but if you add cobalt into nickel, you can decrease stacking fault energy. So if you take pure nickel, if you go to the lowest temperature, it will only have dislocation slip. There will be no stacking faults, no twins, no transformation. But if you combine it with cobalt, say the alloy which we studied cobalt nickel alloy. So if you combine it with 70% cobalt, 30% nickel, so you can have phase transformation at low temperature. So this is kind of thing which is a specific element and the combination which ultimately describe like how they will, what it will lead to. And so stacking fault energy, I mean, because we usually, of course, we study different kind of systems and people add, for example, if you add nitrogen, a very, because it is also a field of interstitial high entropy alloys, right? So you add, say, these small atoms, nitrogen. So if you add nitrogen, to a high entropy alloy to a steel,
Mm.
the stacking fault energy will increase. So a steel which can have, say, twinning or phase transformation during deformation, that will not happen if you have significant nitrogen inside that. So this is so you can really modify which kind of mechanism they can show, and
Yeah.
it's really
Mm.
what engineering alloys
Yeah.
it does. But the point which I would like to make is because I work with temperature changes. So what happened with temperature changing?
Mm.
So I work with cryogenic, but I also work with high temperature. So if when you decrease temperature, stacking fault energy decreases.
Yeah.
So that's why, for example, Cantor alloy, which only have dislocation slip when we deform at room temperature, but
Mhm.
when you go to say liquid nitrogen temperature, 77 Kelvin, it can have deformation twinning and it can have stacking faults.
Yeah.
Similarly, we can have say 316 L steel, an austenitic stainless steel.
Mhm.
It have the same thing. So room temperature, it have very high stacking fault energy, around 60 millijoule per meter square or so.
Mm.
And at room temperature, it have only dislocation slip. But when you go to cryogenic temperature, we did experiments at 15 Kelvin, and it completely transforms first to HCP epsilon martensite and then to alpha alpha prime martensite. And at the end, you have only martensite. FCC is completely gone.
Mm.
So stacking fault energy can be influenced significantly just by changing temperature. So similarly, if you go, there is a material which have some kind of mechanism, but if you go to high temperature, so at high temperature, even those which are showing twinning at low temperature, they are gonna now having a creep or like this green boundary sliding or those kind of mechanism, but you are not gonna have say twins at that temperature. Of course, which kind of system you are studying there, but
Yeah.
in a very simple way, stacking fault energy can be can depend on temperature, and the lowering temperature, you can lower stacking fault energy, and you can have different kind of deformation mechanism which can activate and they can interact, and that can ultimately lead to better strength, or maybe they can prolong ductility.
Mm. Yeah. Yep. And the same occurs when you go to higher temperature. It is FCC materials that are dominant. Again, nickel-based super alloys. So FCC is the structure both when you go very low and when you go very high. Is that the rule of thumb?
Um, I mean, I would like to say yes, but I don't think I should say that. There are people who work with refractory matters because they are the material of choice for high temperature. You're right, because we do use nickel superalloys, which are FCC, but they are not just FCC. They composed of gamma prime precipitate.
Yeah.
So basically, these are precipitates which are giving them better properties at high temperature.
Yeah.
But for example, tungsten is used at high temperature because it can sustain its strength to much
Yeah.
level. Similarly, other
Molybdenum.
exactly molybdenum, tantalum. So these are the materials which perform better because by design, by
Yeah.
the point of their crystal structure, they can sustain, they can retain strength. Because if you look at, say, single phase FCC, say, austenitic stainless steels, right? 316, 304, or you can take tantalloy, which are single phase FCC. If you go close 600 degrees centigrade, almost everything will be flat. I mean, like it's going to come down.
Yeah.
So they lose their 600 degrees centigrade is a bit reasonable up to that, but beyond that, they cannot perform, they lose their strength. But beyond that, you have to have either precipitates, like how you mentioned about nickel superalloys, or we have to go for these refractory alloys, which can maintain their strength to much higher temperature.
Yeah. Or you go single crystal.
Yeah, of course.
And lose everything, but it doesn't change. Mohammed, where are we now in the development? Are we just at the very beginning of understanding this, or is this very mature and you have to look for something else in a few years?
Right. So I don't think I will be looking for something else. I hope not.
Yeah.
So because I mean we are really just starting into this hydrogen-based economy,
Mm-hmm.
and we do have critical climate change. And so we will be working with these materials, which will be at cryogenic temperature. Similarly, the applications which I mentioned in medical field, in energy sector, in aviation, even in our labs, they are
Yeah.
not going to go away. So
Mm.
actually, there will be more, I guess, in that sector.
Yeah.
So I think this is a field which is it have a renewed interest because if you really look at cryogenic materials, they were very well studied during 50s and 60s.
Mm-hmm.
And what was happening during 50s and 60s, that was space race.
Yeah.
So there was a huge driving force during that time. So sometime I think about something and I look into very old papers and you will find something people which have
Mm.
studied during that time and then they were forgotten. But now during past almost a decade or so since 2014, there is a renewed interest, of course, in high entropy alloy because of cryogenic, but now people are studying all kind of materials at
Yeah.
cryogenic because it seems
Mm.
like they can be, or similarly, fusion, for example, because I hope like it can be a reality very soon,
Yeah.
sooner than later. So that can, of course, have huge impact.
Mm-hmm.
And then we do have to, so we study these materials to understand how they behave. For example, I do in situ experiments to see which kind of mechanism they
Mm.
involve. So we
Yeah.
study these to understand how they behave so that we can engineer them for a better functionalities
Mm.
so that we can make alloys which can be stronger and more durable and
Yeah.
which can last longer because ultimately everything is about cost, about safety, and for that you do need these kind of materials
Mm.
to work at such low temperature.
Yeah.
So I think it's really a field which is I guess starting at
Mm.
least restarting if I
Yeah.
have to discount for 50s
Yeah.
and 60s.
Mm.
So I think in my opinion, it have a long way to go.
Yeah. Yeah. Adding to that, I have my last technical question today. Then I promise I'll let you go. Uh, when you talk a lot about the hydrogen era coming, hydrogen embrittlement is also an issue, and a lot of people say, but the high entropy alloys, they're also a branch of high entropy alloys that are not affected by hydrogen embrittlement. Are we combining things here? Are we so lucky that the same alloys that are not affected by hydrogen embrittlement can also be used for cryogenic temperatures?
I mean, that should be the logic, right? I mean, we need material which would not become brittle by
Mm.
hydrogen and also would not at low temperature because at cryogenic temperature, they will also not become brittle. So of
Yeah.
course, that's the ideal situation. And uh, this is the field which we just start. I mean, hydrogen is a very old problem. It's a century-old problem, if
Mm.
not more.
Yeah.
But this, because now we're at a stage where we really need materials because of these applications.
Yeah.
So there is a renewed interest, and people are studying both arsenic stainless steels as
Mm.
well as FCC high entropy alloys for the same purpose.
Yeah.
But it's again like if something is there for a century, so it means it's a difficult problem to handle. How like so
Mm.
hydrogen absorption and desorption, and so I think there is a lot of scope in this area. And you rightly said like we would need materials which can sustain both of them if we have to put them in such applications.
Mm.
And hopefully we will have battery candidate which can be applicable under these conditions and perform in these applications.
Yeah. I agree. I'd I don't understand it myself, so that was why I asked you the question. But
Yeah,
I can hear that we haven't solved all the problems yet. There are still a lot to do, also for youngcomers. So the metallurgy is absolutely alive.
yeah.
Uh, Mohammed, if people want to learn more about cryogenic environments or material in cryogenic world, are there conferences, are there books, are there papers that you recommend?
Right. So there have been book series which was okay. There is one journal. I mean, of course, like now you find publication in every kind of journal published on cryogenic materials because now it's a very famous in metallurgy, materials science as well. But there used to be series of books on cryogenic materials, which I consulted when I was starting this field. So I consulted some of those, look at like what they did. Similarly, there was I think still it might be a journal called Cryogenic. Uh, so that could be another thing.
Yeah.
Then there are like so many publication which comes out about cryogenic. But I would also say that there is oldie papers from 50s, 60s, which exist there when people were studying. There is a database which was compiled on all kind of alloys. I think that was by DOE. I forgot its old name. Now it's the Department of Energy. So they compiled a database of all the materials which was studied until 60s. So that was, I think, published in 1968. So it had all kind of materials. So when I found out, I mean, I put number of figures from there in my thesis introduction chapter. So it's really, really impressive. And you look at that like, wow, like these people compile and they did so much work at that time. So I think those kind of things are the best references and really look at like which material can be used for cryogenic. And also it's very important because we don't have to start from scratch. We have to dig into old literature and we have to, for example, I'm talking about this was a monogram, which was published in 1968 by Warren. So, and if we really look at that, we don't have to redo those things which was already done and which are established. Maybe you can build on them so that we can move forward.
Exactly.
And similarly, so I think it's a very good thing that we still now, especially in the time of accessibility of internet, we don't have to go to library actually, and those are available online. We just have to search for it, and they are there. So I really benefited from these old references, and I really enjoy that how much work was done and how we can take it forward.
Thank you very much. I really enjoyed our discussion, and this is a very new world for me. I'm on my daily basis working on high temperatures, so high temperature corrosion and those kind of things are far away from where we were today. So thank you very much for helping me growing my learning curve.
Likewise, it was a pleasure to come on Everyday Metallurgy because it's very important to communicate about science and really talk about these kind of things. And also, this is two kind of extremes. So high temperature is one extreme, and then this is cryogenic temperature is another extreme of materials. So yeah, thank you so much for having me on Everyday Metallurgy.
Yeah, thank you.